optimizing the decision threshold. So in other words, pick Z. So the idea here is pick Z, minimizing probability of error. And the point to which we were last time was the following. We argued that Oct1-c of X what Oct1-c is defined as is integral from X to infinity of two over pi e to the minus t squared dt. So I don't know what the indefinite integral is, but I could just treat it symbolically. So let's say the indefinite integral of 2 over pi e to the minus t squared dt is equal to f of t, capital F of t. Then this integral is equal to capital F of infinity minus capital F of x. The reason why I don't really care what capital F is because I don't want Oct1-c in this case. What I want to do is I want to differentiate Oct1-c. D by dx of Oct1-c. And that's equal to d by dx f infinity minus d by dx fx. So what's d by dx of f infinity? That's just a constant, so that's 0. D by dx of fx, well, what's capital Fx? That's the indefinite integral of this. So because integration is the opposite of, integration is the inverse of differentiation, if I differentiate this, I should get that back. So this should be equal to minus 2 over pi e to the minus t squared dt. E to the minus t squared.
Root pi?
Yes, root pi. Just one other thing, this is sort of where we were at last class, which is if I have Oct1-c of not x, but some function of x, 5x, then d by Oct1-c, d by dx, Oct1-c of x, Oct1-c of phi x, is equal to, this is the differentiation chain rule, d by d phi, Oct1-c of phi, times d phi by dx. Or d by d phi, so that just treats this phi as a variable. That is this, and then we multiply by d phi by dx. So that's just thinking back to first year calculus. Okay. So, what did I want to do? I wanted to maximize, or excuse me, I wanted to minimize probability of error with respect to z. And average probability of error is a function of z, so what I do is I take the first derivative of probability of error with respect to z, and I set it to 0 to find the critical point, and then I get my solution. So d by dz of probability of error is d by dz of 1/2 Oct1-c. That's 0 minus z, 2 sigma squared, times probability of 0, plus d by dz, 1/2 Oct1-c, z minus s1, root 2 sigma squared. squared. There's probability 0. Okay, probability 1/2, probability 0, excuse me, that's probability 1. 1/2 probability 0, 1/2 probability 1, those are all constants, so they come out.
So you single square root over 2 over single square?
Oh yeah, thanks. So I have 1/2, probability 0, d by dz of C, that's 0 minus z over 2 sigma squared, plus 1/2, probability 1, d by dz, curve cz, minus s1 over 2 sigma squared. Continuing at the top of the board. Actually, no, I'm going to keep this up for a second. This is equal to 1/2, probability 0. Okay, what is this? This is, this looks like that. So if I say phi of z is s0 minus z over 2 sigma squared, then d by dz of that is, remember, d by dx cx is 2 over root pi times e to the minus x squared. So here I have 2 over root pi. This is kind of complicated, so I'm going to say x.
You're missing a negative?
Yes, you're right. This is minus, I'll take the minus up front, minus 1/2, probability 0, 2 over root pi, x of minus, that's 0 minus z over 2 sigma squared. Am I done?
Square.
Root 2 sigma squared. Am I done with this? What do I do next?
Don't have to square.
Oh, I have to square this, that's right. What do we do next?
Oh, then you have to also take the derivative
I have to take the derivative of this with respect to z. So this is the phi, and now I have to take d phi dz. So what's the first derivative of this with respect to z?
1 over root 2 x squared.
Yeah, it should. It's actually minus 1.
Minus
minus
1
here,
over
so
root
it's
2. What's the other minus?
minus 1 over root 2 sigma squared. Okay, same thing over here. Yeah, this minus cancels with that minus. Okay, plus 1/2 probability 1. I do the same thing here. D by dz over c is minus, so that minus will come out front. 2 over root phi x minus z minus s1 over root 2 sigma squared times, now it's plus 1 over root 2 sigma squared. Okay, let's rewrite that at the top of the board.